Good morning. The presentation you are about to see has been prepared using Resonite, a VR platform, free to all. You can all enjoy this virtual world here we have put together, either by using a VR headset or directly using your desktop or laptop computer. The presentation is delivered by Joe Ibrahim. Joe has finished his PhD thesis at the University of Sydney. And part of his work was done in collaboration with Donna Whitney and Christian Tessier from the University of Minnesota, and collaborators from France, Françoise Roger, Valérie Boss, and Bénédicte Senki. My name is Patrice Ray. I'm from the University of Sydney, and I hope you will enjoy this talk.
Hello, everyone. My name is Joe Ibrahim, and welcome to the first talk from the metaverse. This is a kind of weird talk, so we're going to look at some kind of weird geology. So, what we're looking at is the intercratonic orogeny in Central Australia. What we have here is an origin deep in the middle of a craton, far from any active plate boundary. And this was also the case during the Alice Springs orogeny in the Paleozoic, when we think these structures are formed. So, let's zoom in right here to the middle of the continent. And what we have is this interesting juxtaposition between a nice dome known as the Entia Dome and a series of fallen thrust belts and naps known as the Rarotonga Nap Complex. Now, because we're in VR, what I'm going to do is fly up to the top of this world and look down at the satellite image, and we can have a look at the geology, figure out what these structures are doing in the middle of a continent. So, let's go. So here we are at the top of the world. This is looking a bit wonky because now you're looking through my eyes and these are my hands. And we're staring down right at the middle of Central Australia, right there on the Earth. And because we're in VR, what I can do is pull the slider to reveal the geologic map underneath. And so there's the Entia Dome, there's the Rarotonga Nap Complex. And what's really interesting here is these colors in yellow, red, brown, and blue were once all thought to be formed in the Paleoproterozoic. The protoliths of some of these rocks are dated to about 1.8 billion years ago, and we thought most of this stuff formed in the Paleoproterozoic. In contrast to the south in our folding thrust belts and naps, we thought most of these formed in the Paleozoic, and they're comprised of these Neoproterozoic rocks. And then the big discontinuity between the two is the logwith shear zone. So we thought the logwith shear zone separated these two domains. But then in the last 10 years or so, this entire understanding was flipped on its head when we found out that the Hartz Range metamorphic complex, the rocks that make that up, are actually just the high-grade metamorphic equivalent of the rocks found in the Ruby Gap Duplex. So because of that, we've realized that maybe this stuff hasn't formed in the Paleoproterozoic like we thought, but instead might have formed at the same time as the Ruby Gap Duplex. So our goal is to go into the field, take you with us because we're in the virtual world, and we're going to do a cross-section from the dome to the duplex. We're going to have a look at the logwith shear zone. We're going to look at the structure. We're going to do some geochronology, and we'll see if we can come up with a story here. Here I am flying over the Entia Dome. So, the Entia Dome is a double dome separated by a median high strain zone. It's comprised of the Inkamula and the Hakata subdomes, with protoliths aged about 1770 to 1760 MA. Let's have a look at some outcrops. I'm going to fly in. We're going to look at an outcrop right there in the median high strain zone. So I'm just going to fly through here, and we're going to have a look at this outcrop. Well, I hope this isn't too disorienting for you. So what we see is this migmatite, and this migmatite has been folded into these nice upright folds that we see here. And then we decided to do some targeted geochronology within the leucocratic veins here. And what we found was a monazite age that gave us about 314 million years. Moving through the landscape here, we start seeing more of these horizontal folds, and when we send the drone out, it takes these really nice images of these landscape scale horizontal folds. So here I am, I've teleported, I'm standing on the rim of the dome in this high strain envelope. And what we're looking at here is this titanite vein that was refolded by these horizontal folds. And we dated that and got an age of about 315 million years. So these ages here and the structures we see tell us that the dome likely formed in the late Alice Springs orogeny during the Paleozoic and not during the Paleoproterozoic. So here, as we move to the southwest, just on the rim of the dome on the edge, what we come across is the Harding Springs Slide. Now, this is a large-scale normal fault. And what we see, this really strong down delineation. It's an LS tectonite associated with a normal sense of movement. So when we move a bit to the south past the slide, what we come across is the Bruna gneiss. The Bruna gneiss is a very mesmerizing rock. If you stare at this rock, it stares back at you with 1,000 different eyes. And here we generally see a top to the south, so that's that way, sense of shear. Though signals could be pretty mixed. So this rock is about 1.8 billion years old. We imagine it's been through some history. Here are some more outcrops of the Bruna gneiss. Here we're looking along the kinematic plane, and we can see a nice top to the south movement. And then we also see these other structures here that imply that there's likely some pure shear happening. And the scale here is accurate. This was just incredibly large. So we thought we'd share that with you. And now we'll just continue moving further south and go into the Ilagua shear zone, what was thought to be the big discontinuity between these older and younger domains. So here I am in the Ilagua shear zone. What we see is this really nice down dip lineation. When you have a look at SC myelinite, it gives us this nice sense of shear that is top to the south. It gives us a thrust kinematic. And as we look around, we see more outcrops that show nice consistent down dip lineation. In terms of metamorphism, grade has been decreasing. So here we're looking at muscovite and even chlorite. And looking off in the distance, here we see the ruby thrust. So this is the first fold and thrust belt we come across on our sequence. And this is the Ilagua shear zone here. And even just from the view into the landscape, it looks like they're in structural continuity. It looks like everything is nice and in harmony and structurally congruent. And just before we head to the Ruby Gap Duplex to the south, some geochronological work has been done in the area by the Northern Territory Geological Survey, and they got an age of about 327 MA from argon-argon on muscovite, showing that this was also likely active during the Paleozoic Alice Springs orogeny, and that these ages aren't too far from what we saw in the dome. Now, moving into the Ruby Gap Duplex, what we have are these Amadeus Basin sediments. We have the heavy tree quartzite, and it forms these really nice massive walls. Then we have the Bitter Springs, which is exposed as a dolomite here, and we get these really nice folds, and some basement rocks underneath as well. So let's have a look at our structural interpretation. What we've seen is structural continuity all the way from the dome to the duplexes down in the south. And in the dome, we see the double dome with the cascading folds and the upright folds that have been refolded in this constrictional high strain zone. And that goes nicely into the normal fault, which isn't quite shown here, but we have these shallow dips into the fold and thrust belts and duplexes further south. So we've seen that we have a structural continuity from the dome to my left here to the duplexes that we see. But what brings it into the middle of a continent? And what's even more interesting is this is what we thought this part of the world looked like before we had the dome. We had a rift basin filled with about 35 kilometers of sediment, and it was this very narrow and deep rift. So what we think the answer is contractional gravitational collapse. Now, to explain what that is, I'm going to go and talk about extensional gravitational collapse first, which I think most people are familiar with. So generally we have this thickened crust here, and because of the gravitational potential energy differential, material will flow out to the sides and we have this gravitational collapse. So in contractional gravitational collapse, it's the same principle. We have this low density region signified by the really deep and narrow rift basin in this case with these lower density sediments, and this higher density regional gravitational potential energy that causes material to flow in from the flanks into this area, and we have this contractional gravitational collapse. We think this may have exhumed the dome, and the fold and thrust belts that we see to the south might be a consequence of this. So this was a lot of geology given very quickly over a very new format. If you'd like to read more about it, it's live in Geology Now. The cover photo here is the Bitter Springs that we saw in the Ruby Gap Duplex with its really nice folds. And today we did a cross-section from the Entia Dome to the Ruby Gap Duplex in virtual reality. We had a look at the kinematics and we looked at some geochronology. If you have any questions, feel free to reach out. Thank you.